Here, Pushover analysis. Then, as I told you, at some increment, the system gets into nonlinear range, or the sum of the cross sections, the moment becomes is equal to MP, and there is a yielding that takes place. Okay. Now, if I have to do that, I have to catch basically how the yielding takes place, and after that, what will happen? I have to define something called a backbone card, which is called also M theta card. M theta means moment rotation card. And any software, if you use for nonlinear analysis, you will find they are asking for a M theta curve to be specified, and if you don't do that, they have a default M theta curve defined, okay, and they use that default M theta curve. Now, this M theta curve means when you start calculating, and initially it assumes that all the members are elastic, okay. And in elastic range it has a stiffness, and according to that stiffness it generates the stiffness matrix, and then go ahead with the calculation. Check at every cross section whether MP has reached or not, and once MP has reached, then what it says that here yielding has taken place, and this particular section now will behave in a particular fashion. Okay. There are a few possibilities for that. Since these behaviors should be, in principle, should be given according to some experimental test, M theta curve. That means you should see actually once the MP has reached, then on further application of the load, how moment versus theta that is occurring. And that experimental M theta curve actually is shown here. Oh, sorry. Here. This is the M theta curve. Various forms could be there, and you can see that up to certain portion it is linear, and then after that it goes up like that, then it goes down, and this shape could be, many kinds of shape could be there depending upon the joint or the cross section that you are testing. So what it means that up to this you do a linear calculation, okay, for the particular cross section, and then once this MP is reached, then for further theta MP relationship is governed by this curve. Okay, so you calculate theta first from the displacements, and once you calculate theta, then from the curve you say this is the value of MP, or MP, sorry, not MP. And you can see that this does not necessarily flatten like this second curve. That means it can go up, then it can go down. It can take up many shapes. But this particular information should be provided, because after yielding of a particular cross section, what the moment it can carry, that depends upon this backbone curve. Now, usually, many times this particular thing is not available, okay, and we are not able to provide the actual backbone curve, right? So in that case, there are certain options that this is a backbone curve. This is slightly more stiff. In the drawing it has become more elastic, more stiff, and from there it goes like that. So this kind of card is given in the softwares. And there is a ratio. That means this slope to this slope, there is a ratio they maintain, maybe 1:10, 1:12, this kind of ratio that is maintained over here, and this curve is given. That means after the yield movement is reached at a particular cross section, it is not remain MP, but the increment is very small, very MP small, I mean very marginally MP moment increases. The other one is elastoplastic. Elastoplastic means that is a very common assumption in inelastic analysis we do. That means it remains elastic, and once the MP is reached, after that it is no more capable of taking any further movement into the system, further load, that particular hinge. Okay. So there, this particular idealization that I said before, that once the plastic hinge is obtained, then you say that you replace it by ordinary hinge. That means it cannot take up movement. That is valid for this kind of backbone curve, right? So, unless you are using any software, unless you have this third one, if you want to write a program of your own or make some analysis without having these curves, then you can use this elastoplastic. An elastoplastic assumption is a very, very common assumption in elastic analysis of structures. Right? This is called the backbone curve. In the first two curves, as the calculated M at a section MP, there is a mild or no increase in M for further rotation. Hinges that are described above have, except for the second model, M after yielding is read from the curve. For the second one, M is equal to 0. Sorry, M is equal to MP. It should be. M will be MP. For the second one, M will be theta greater than theta C. Okay. So that's about the backbone curve. Okay. So these backbone curves are necessary to find out or to carry out a pushover analysis. Now, when you are trying to do a nonlinear dynamic analysis, you have to also provide the same information, cross section. And what the computer does, or you may be writing the program, in that what happens, there is a hysteretic loop at a particular hinge. This hysteretic loop is because of the reversal of the loading. Reversal of the loading means here we are talking about a monotonic increase of loading. Monotonically, in one direction I am going. I am not reversing. The moment I reverse, what will happen? If the displacement has gone up to that, then from here if I unload it, it will not follow this path. It will straight away come like this. And if you go below this, this will be like this, and it will create a hysteretic loop. So there is a difference between a pushover analysis backbone curve remains the same, but in the pushover analysis, these hysteresis loops don't appear. But in the dynamic analysis, we find that because of these kind of backbone curves, hysteresis loops are provided, are obtained. And this hysteresis loop would not appear if we say that it is just linear like this. It's just linear like this. Then the up and down it will be going like that. That is the linear analysis, linear dynamic analysis, linear pushover analysis. Okay, in that this business of shifting after the value of MP, that does not come into picture. Okay. So this is another important thing. Remember it in connection with the pushover analysis. So hinge property is described by a curve called the backbone curve or M theta curve and is determined from experiment test of joint. Non-linearity is performed over with no backbone curve specified and curve specified. The default backbone curve is assigned by the software. Note that ductility is inherent in all backbone curves. So that is what I told you in the beginning, that some of the important property, I mean fundamental things about this PBD is the ductility, damage, plastification that you have discussed, okay? And you can see all the backbone curves are providing a kind of ductility. That means beyond the yielding, still it can, it does not, what we call, immediately collapse, but it takes a time to collapse. क्या हो गया भाई? Now, the last item of the day. No, not last item. अभी तो just शुरू ही हुआ है. Experiment and test for determining the backbone curves consist of reverse slow cycle pushover test. ठीक है. इसका बाद ही वो दिखाएंगे एक मिनट. अब बाद में दिखाएंगे. Anyway, this would be shown also to you through the video. Now let's say that we want to obtain a pushover curve, or sorry, a backbone curve. Okay. For say here, say for the say the beam in there, I want to obtain a backbone curve. That's my intention. So I make a frame. I provide an actuator. Do a displacement pushover analysis, right? And give displacements in increments. And we make a full cycle. Now this full cycle means, say I take a displacement of 0.02 centimeter, okay, increment. So I give 0.02 increment in a full cycle. That means I gradually go to 0.02, then come back, then again go to 0.02. That means a full cycle. So this kind of thing I go on doing. Then first 0.02, then 0.04, so next 0.02, next 0.02, and so on. And in each case, what we do, that I give a full cycle. Okay, that's why it is cycling. It is go like this, come back, go like this. This is a full cycle. Now, in that case, we go on finding out the story drift, say. The story drift means here displacement itself. Okay? And displacement and also base shear. All of them I am measuring and trying to plot them. Okay. And the plot would look like this with small increments. If I go for a reversal, that means initially you can see that it is remaining state, it is going like this. But after some time, when the inelastic state comes, right, then you can see that there are the hysteresis loops are generated. Hysteresis loops are generated. This is another hysteresis loop are generated. That means with increments, the hysteresis loops are becoming bigger and bigger. Hysteresis loop. Okay. This hysteresis loop is because that I am going a full cycle and the entire system has gone to the inelastic state. And the moment it comes back, it does not follow the same path. Okay, that's why this is the hysteretic. Then once this hysteresis thing is done up to the full test, then what we do, the top of these hysteresis loops over here, we join them like this, join them, right? For all, these are all the tops of the hysteresis loop, right? This is the tops of the hysteresis loops that I have joined, and once we join them, then this is the backbone curve. Okay, so this is experimental backbone curve. So this experimental backbone curve is taken for that particular specimen, and if I want to do a pushover analysis, then I'll, in place of a elastoplastic one or a default curve, I'll give that dotted line. That is the backbone curve. Okay, so this is the experimental determination, and I have talked about the backbone curve. So an essential ingredient of your pushover analysis is backbone curve. Now next point is that, as I told you, the identification of damage states. Okay. In PVD, that is the most important thing. You are saying that I must have damage up to this level, okay, and I'll design my structure according to that. Okay. I will not permit beyond that. And this is specified before the design, and that is where the design becomes a challenging one. Because before you design, you cannot analyze and you cannot check whether your damage state it is less than that damage state. And you can define the damage state anyway. That is what I've told in the morning, right? Damage state. There are many definitions of damage index and hence definition of damage state. A threshold value or a bracketed set of values may be assigned to an EDP, engineering demand parameter, in order to identify the damage state. EDP also I have told you, and I have told you about the bracketed values or a particular value. Typically, EDPs consider a top story displacement, maximum interstory drift, ductility, maximum rotation at the yield section. Out of these, the last one is adopted for PVD. That is the rotations at the plastic hinge. What is the rotation that is taking place? Okay. And based on that, we usual performance-based design that is there in the softwares. In seismic PVD, 3 states of damages are identified. They are immediate occupancy, IO, life safety, LS, and collapse prevention, CP. These are the 3. These damage states are indicated by color code. I really don't remember. Red, of course, is CP. Blue and green, which one is what I have forgotten, IO and LS. So one of them is, LS is green or IO is blue. I have forgotten that, but red is certainly CP. So anyone remembers, anyone has used?
It is probably in the respective order.
Huh?
It is probably in the respective order.
The order is all right? Huh? Okay. Blue, green and red. At the yield sections, rotations are considered at the damage states. LS indicates theta should be less than equal to theta L. CP indicates theta L must be greater than theta L and less than theta P. And IO indicates theta should be less than theta I. Theta I is your immediate occupancy. Okay. Now, when we do a performance-based design of seismic performance-based design, many people can say that I will not allow performance point to be to remain within IO. IO means immediate occupancy. If an earthquake comes and goes, structure will have minor damages and people can get in easily. That is immediate occupancy. The life safety means, yes, there is damages in the structure, it need to be retrofitted, but there is not much. That means if you go even in the house, the things will not fall down, right? Collapse prevention, last one is that the structure will be heavily damaged. You have to run out, right? And whether the structure can be retrofitted or strengthened or demolished, that is to be a decision taken later. But it does not collapse as such, but heavy damage takes place. Okay. So these are the three states, and accordingly we see that my performance point, which is now our next point of discussion, performance point is within that particular either LS, CP and IO. Another important feature of PBD is to determine performance point on the capacity curve, that is base shear versus top displacement, that I have told you before. CSM technique is used for this purpose. Okay. The central idea of CSM technique is to plot the capacity curve and the demand curve, that is earthquake spectrum, on the same set of axes. And as I was explaining in the beginning, that SASD. In the SASD plot, I have to put both the capacity curve and the demand curve. And the intersection of that basically is the performance point, where we say that capacity is equal to demand. Okay. The intersection of the underlying theoretical basis is the modal pushover analysis rather than the ordinary pushover analysis. Why we have taken a modal pushover analysis rather than ordinary pushover analysis is because of this reason. That means we wish to plot the capacity curve on a SASD, right? That's why I have done that. Now, if I go to the little bit background, I mean, you have not done your dynamics course or the multi-degree freedom system. Now, any system, as I told you in the beginning of dynamics course, that in olden days, the engineers were not having computer, and they were dealing with multi-degree freedom systems. So what they used to do, they used to convert this multi-degree freedom system into an equivalent single-degree freedom system, right? Using their intuition, using their experience, and knowing something about the fundamental frequency of the structure. Okay. So what they used to do is that they depending upon the structure, they used to assume the fundamental mode shape for the tall structure, okay, for a particular building. And many approximations are there in the literature where you will find that they are having a cubic variation, they are having a quadratic variation, they are having a almost linear variation. These kind of variations have been assumed by those people, and that they used to say as the fundamental motion. Okay. This is one thing. Second thing, they had an idea about the total mass of the system and an equivalent stiffness for the system. Okay. This equivalent stiffness, how they used to calculate, that used to depend upon person to person and their own experience and intuition. But people can do it. I am giving you must have Chopra's book or any other textbook in my lecture note also have shown you that say I have a beam. I want to convert it into a single degree freedom system. So I convert it into a single degree freedom system by considering at the center, I lump the entire mass of the beam and say that what is the force necessary to push by unity the center of the beam. So I am considering the stiffness of the system, an equivalent stiffness of the system, by way of defining that what is the force required to provide unit displacement at the center of the beam where I have lumped the mass. This is my basis. It may not be, it may be far away from the actual, maybe, or may not be. But what I am saying that this is how they used to do it. So once you have done that, then you have a K, you have a M, you can find out the frequency of the system. Okay. Now, say for example, if you do this for a particular beam, simply supported beam, you will find that the fundamental frequency of the beam, if you calculate by continuum approach, and this way if you find out, they differ by 10%. Okay. So, depending upon the structure and depending upon your own experience, people could calculate a stiffness, or sorry, a frequency, fundamental frequency, and a mode shape. Once it is done, then you can convert it into a single degree freedom system, the entire structure. Okay. And once you have converted into a single degree freedom system, then the things become simple. Okay. You can plot it into SASD. Now, the normal mode theory in the dynamics, you will see that it is doing that. That means for each mode of vibration, you can convert a system into a single degree freedom system. And here, for the first mode of vibration, or fundamental mode of vibration, by knowing the mode shape and by knowing the natural frequency, you can convert it into a single degree freedom system. That is what is done in the pushover analysis, CSM technique. Okay. Now, for an SDF system, the base shear for a single degree system will be mass multiplied by SA, spectral acceleration. Okay. And hence SA is equal to VB by M. Also, maximum displacement of an SDF is SD. That is the top displacement of the frame becomes SD if it is converted to an SDF system. Okay. And in that case, the basic assumption is that the mode shape coefficient at the top is made unity. Then the top displacement becomes equal to SD. Thus, the capacity curve can be plotted in a SASD curve. How? On this side, you got VB, you have plotted, and on this side you have plotted the SD, top displacement of the building. So what you do, you simply, the mass of the building, whatever is the mass of the building, you divide the VB is divided by that mass of the building, and you immediately get SF. And the top displacement itself become SD. So this plot, the VB versus top displacement plot, can be given in a, you can convert to that. And response spectrum for an earthquake can be plotted on a SASD curve. Now this needs little bit of explanation that I am showing over here. What is the next curve? Okay, fine. This all of you know. This curve you are all acquainted with, which is in the IS code, earthquake code, response spectrum. Okay. So on the one side it is SA, other side it is time period T. Okay. Time period means 2 pi by omega n, or omega n by 2 pi. 2 pi by T is equal to omega n, and T is equal to 2 pi by omega n, where omega n is a natural frequency. Okay. And SA is the spectral acceleration. And the definition of the spectral acceleration is SA is equal to omega n square ST. So you can get SD as SA by omega n square. Okay, these are all fundamental relationships. So you are given SA. You can find out for each value of T or omega n corresponding SD value. It's all right. 2 pi by T is omega n. So, for different values of T, you can get SD. So you can have a plot of SD versus T. Say this is a plot something like this. All right. Now in these two plots, what is common? What is common? Time period common. T is common. So what you do, you can remove T, this common. So therefore, you take any value of T. Say if I take a value of T over here, I know SD, I know SA, so I plot, if this is SD, this will be SA. So I get that point. Then for each T, I can find out a pair of SA and SD that I can plot, and that gives me another kind of spectrum, SA by SD. This is called bispectrum. Okay. So you can see that response spectrum of the earthquake, that can be plotted on SASD curve. And if I join any point This point shows nothing but SASD combination that gives me a particular value of T. It occurs for a particular value of T, that particular point. Alright. So this one I can plot by SASD capacity curve. I have divided V by M, it has become SA, and top displacement itself is SA. So I have a capacity curve plotted on SASD, and the response spectrum is called demand curve. Why demand? The earthquake is putting a demand on it, on the structure, that this much force you have to withstand. So that is its demand. So that's why it is called a demand curve. So these two are now plotted in a SD plot. On this side it is SA, on this side is SD. This is your the response spectrums, and this is the capacity curve which you have plotted on ACSD. Okay. And this point where it cuts, this is your performance point where capacity is equal to demand. All right. And what you do is that at this particular point, you have plotted capacity curve. So when you have plotted capacity curve, you know base shear. If you know base shear, you know the moment, you know displacement, you know any response quantity. So you have that idea. Okay. And if you say that my performance point should be such that it will not have exceed IO level. That means practically it is remaining in the elastic state, practically, not very mildly it might have gone into the inelastic range. But if you say that no, it will remain in the IO to LS range, that means under that bending moment, shear force, etc. combinations, the structure has gone into an inelastic state, but that inelastic state is not very highly significant inelastic state. Okay. So life safety is ensured. So that kind of thing is done in a performance-based design, right? So key is that you are using CSM technique to have a performance point, define the performance point, and for the performance point, see that if the inelastic state has reached, then what is the state of that inelastic state? This inelastic state, whether it is in the LS state or IO state or CP state. Okay? और कुछ है कि नहीं देखता हूँ. Yes, this is the last slide. Last story of the thing. So the backbone curve that I have shown, that is now experimentally how you can obtain. Downstairs in the laboratory, we carried out a test, and all these guys, your Sam Saab, this Saab, that Saab, Bharati Saab, and all these people are working day and night to make this lab do this kind of 3-4 tests have been already done with an actuator and all that. All of you, those who are interested, at some free time you can go and visit the lab and see actually how these kind of tests are done, pushover tests are done. So I'll do some magic first. Let me see. Mohit. Yeah. So you can see that the cycling motion is taking place, isn't it? So you can see there is the actuator. Actuator is there. This is the actuator which is pushing. Okay? On the top. And this actuator is connected over here at the center. And it is pushing. And this is a reaction valve. With this reaction valve, this actuator is fixed to this reaction valve. The moment it is pushing this building, there is a thrust on this wall. And this wall is able to remain almost rigid. That is how it has been designed. Reaction valve. Okay, so in the beginning, small displacement, and when it was going, it was following more or less the same. Okay, then gradually deviated, and then you can see the loops have started forming. For bigger displacement, loops have started forming. Can you see that? Okay, and then if you join these points, this top of the points, then it gives you the backbone curve. Okay? So that's all I think I had to classification, everything. And this I think were a fundamental thing to what Professor Sinha is teaching to you, and you will want to know more about it tomorrow from him. All right? So now if you have